Welcome to another video explaining the universe using the particle model. Today's video is titled The Ultraviolet Catastrophe, a preliminary analysis. My last video was about the ultraviolet catastrophe and proposed that maybe the particle model could provide some answer to that. But before we get started, I'd like to have a little short presentation about the book that Dave and I have written. Yes, that was the logo of the book. It's a double apple. You can buy the book on Amazon at hardcover, paperback, and ebook. And yes, the title is Principia Mathematica 2. I did a previous video, and you may want to watch this video before you continue with this one. And I'll list this link in the description of this video. And all I did was try to do an analysis of how this might be solved without using quantization. A little bit of background first for those of you who haven't. This is the ultraviolet catastrophe comes about by measuring the spectral radiation of radiation coming out of a black box. And in this particular video, this person is setting up 3 black boxes. Each black box is hollow and has a black hole at the center of it. And when you look at it this way with normal light, you just see the color of the box, and they're different materials, and you don't see anything coming out of the black hole, and that's why it's called blackbody radiation. Well, if you look at it through a infrared gun, you get this picture. The surface of each body does emit of its own. It's just sitting there emitting infrared light. But where it was totally black, you get high intensity radiation. And what is being measured is the radiation coming out of that hole, and seeing what frequencies it is generating. So this graph is actually helps explain the catastrophe. This is the spectral radiation here in kilowatts per steradian per meter squared per nanometer. And the horizontal axis is the wavelength of light in micrometers. And typically when you do a real good test, you heat the black box to a given temperature, like 5,000 degrees Kelvin or 4,000 or 3,000 Kelvin. Keep in mind that room temperature is 300 Kelvin approximately. And so they measure it and they get these 3 curves, which is all well and good. Well, the physicists at the time want to develop an equation, a theory about this, and they get this curve. And the problem is this curve tends to infinity when it gets to 0 wavelength. Of course, you can't have a wave with 0 wavelength. That doesn't make sense, and that's why it's 0 down here. But it's called the catastrophe because classical physics could not explain it. Well, Planck in 1900 got into the act, and he developed an equation for the energy being emitted. And nu is the Greek letter for frequency. You could just as well put an F there. And H is Planck's constant. Not going to go into all of this, except that he used this equation and it doesn't solve the problem. It didn't get an answer to further catastrophe. There's no explanation why the curve comes down at high frequencies. Well, Planck then discovered that he could derive a better equation, but only by making what he considered to be an outrageous hypothesis. Yes, and that hypothesis was that for a mode of frequency, for one frequency, the energy of the cavity can only exist in lumps of quanta of size E equals HF. Everything comes in the chunk. One of these, two of these, three of these. And he asked then the question is, how does this avoid the ultraviolet catastrophe? Here's his thought. And by the way, he's very close to what answer I'm giving here, but he doesn't get there. It says even a single quantum for a very high frequency mode would be huge. In other words, he's saying there's a problem if you have one quanta at a high frequency. The probability of it occurring would be huge. Actually, it sounds reversed, but he's into the idea that the amount of energy at high frequency would be a problem. The chances of great chunks of the available energy going to more than a few, yeah, this fixes it, more than a few high frequency modes were remote. In other words, he says it can't happen. These greedy modes were priced out of the market. What he means by that is when he quantized it, he eliminated those greedy modes. And what he did, took his simple equation and added an integer number n, which has a value of 1, 2, 3, 4, so that the energy of each quanta of light that was emitted was a multiple of h nu, and allowing only the integer values. But he has no physical reason. That's why this is an outrageous assumption. He has some thought about that it might help, but he can't quantify the physical basis for it. Well, this was a previous conclusion I made from my last video, and I said, well, I get it. The ultraviolet catastrophe occurred when there was no real model for light. I might have done the same thing, but now we have one. TPM light gives enough physicality to provide a better answer. And this is what leads to this particular video. One possibility is that I used TPM to generate an equation for the spectral energy, which includes, I hinted at this in my previous video, which includes intensity and the size of light and anything else that I needed. So I did, here I'm applying TPM light. And those of you who have followed this very long know that TPM light is made up of G1 particles. Peaks of light, G1s are clumped together, grouped together here and here, and from peak to peak, and the spacing between the two peaks is the wavelength. And so this could very well be red, green, or blue light in its simplest form. Well, here's a diagram of the cavity. This is not a box this time. It's a circular cavity. By the way, it has a double wall with an evacuated in between the wall to help stabilize the temperature, and they heat it up to 5,000, 4,000, 3,000 Kelvin, or whichever they want to. And the inside of this cavity generates, in this case, this picture says it generates photons. So you got spontaneous photon emission inside the cavity, and the photon hits and bounces around. And even though it may be very high energy to begin with, by the time it gets through bouncing around, scatters, it gets reduced and reduced, and Some of them may never get out, but some of them finally come out and are emitted, and that's what's measured. Now, in the case of the particle model for light, the reason that this stream of light like this is being emitted, if we're at 5,000 degree Kelvin, all of these atoms and molecules in this wall are vibrating at the same rate. Very stable temperature. They're vibrating at the same rate, and as they vibrate, they hit each other and they release G1s in either big clumps or little clumps or almost no clump. But typically they're going to have a typical energy distribution that the TPM sends out. And these clumps, these peaks, will hit a wall and lose some of the, and hit another wall, and until they come out. How they come out, if they were, let's, for an assumption that they're kind of all red, just to give it frequency, and you'd think then that they would all come out nice and red. Well, the problem is these take different paths. If it only bounces twice before it gets out, it's going to be very high intensity. And secondly, it may match up with another one that bounced around a little longer, and their frequencies don't match anymore. And so you get a mix of peaks that are all, or don't match the original emission. So you end up with random peaks coming out here, and that's why you get so many different wavelengths or frequencies. And I'm going to concentrate on this 5,000 degree Kelvin curve and see whether I can at least empirically match that curve. Now, the peak size that comes out, temperature of a black body determines the maximum peak size. At 5,000 degrees Kelvin, assume that the peak size maximum is 100. That's the maximum. And I'm assuming that coming out of that small hole, that the distribution, that there'll be one point where there's a maximum number of that. That's only 6.27% for this curve. I've actually worked on this curve and worked with the actual values here. 6.27% of all the emissions would be at this point. When you add up all of the percent of each one of those, you get 1. Sum of all occurrences in a probability distribution is 1. But the reason I picked this skewedness is because, number one, there's an absolute maximum determined by the 5,000 degrees. There's a mode. This is its main mode. And because of all the bouncing around, you're going to get a lot of lesser ones. So it's not a bell-shaped, a perfect bell-shaped distribution. It's skewed, actually negatively skewed. So I'm going to use this value of 80 as my typical maximum, and I'm going to plot a curve of peak size based on a distribution like this. Now, before I do that, let's talk about a couple of concepts I'm going to use. There is a question about a detectable peak. That is, how small can the peak get before you can't detect it? Very small peaks cannot influence your eye or a detector. Now, each peak here is about 15 or 20 little G1s, and as they bounce around, it gets smaller and smaller until, well, maybe you only have 1 G1. Okay, according to the particle model, I can guarantee you don't see 1 G1 because that's what the gravity field is made up, and that's happening all over and right in front of me, and I can't see it. And they can even hit my eye. You don't see 1 G1. But so one of the criteria for the wavelength is that there has to be a spacing here. the spacing between this peak and this peak has to be a certain distance. And if R is 1% of this wavelength, I'm just giving an arbitrary limit. I'm saying that the intensity is not detectable, and there is a lower limit for which your eye or the detector you're using cannot see it. That's a lower limit. But now the detectable wavelengths, I'm saying there has to be a certain amount of space. Peaks, which are groups of G1s, must be separated by the minimum length of 1/2 lambda. That's me saying that. Don't know that's true. I'm just trying to quantify this in some sort of understandable way. You may disagree. You may say this needs to be bigger. You may say it needs to be smaller. But there's a limit. It must be separated by a minimum length. Here I'm saying 1/2 a wavelength. If the peak is large, greater than 1/4 of a wavelength, then this peak is going to be big, and it's going to shorten the D, and this peak is going to be big, and D is going to be smaller. And I'm saying, okay, there's a peak, there's a distance between them, but it's not detectable. And this is very critical at where the ultraviolet catastrophe happens. On the other hand, you can have any number of smaller peaks. It can be equal to or less than 1/4 of a wavelength. As these get real small, you got a bigger space, relatively speaking, and that's detectable. So these two peaks would actually generate some sort of square wave, actually, if that hit a detector and you measured it, put it on an oscilloscope. You make these very small, and you're going to have a small pulse here and a smaller pulse here. But a detectable wave has peaks of a radius r of 1/4 of a length and a distance d of 1/2, and that's the criteria. Point being, if the peak is too big and you're at a high frequency, this is what Planck was saying. Peak was too big at a high frequency. It can't happen. I'm saying you can't detect it because there's not enough space between them to discern that it's a wave. That's a further explanation of that. Okay, so the maximum peak size I picked was the maximum. There's 100. There's the mode of 80. And we know that as the wavelength gets bigger, that's what this, no, it doesn't say wavelength here, but as the wavelength gets bigger, you can allow larger and larger peaks, and maybe even larger than that. But the only reason it doesn't go any higher is because we're sitting at 5,000 degree Kelvin. It's only generating a certain size peak, and then it gets less from there. So there is a limit as to how big the peaks get out here, even though in other cases the peaks could be bigger. But when you go down here this way, you're at a high frequency, a short wavelength, and because it's a short wavelength, the peak size has to get smaller and smaller and smaller, and that's what I'm doing here. This is a linear scale. This is a linear drop-off till you hit 0, where you hit this minimum detectable peak. Down here, there's two problems. You can't have a wavelength with a wave with 0 wavelength, and so you got 0. But then when the peak size gets so small, you still can't. It may be there, but you can't detect it. So this is the maximum peak size representing intensity by wavelength. Okay, now I'm going to go to an equation. This is the equation that I've developed, that I'm saying that the energy, in this case, is potential energy. It's not the actual energy that hits the detector or hits your eye. I don't have that information to deal with. But I have a peak that has G1, it has G2 mass, and it's moving and at a velocity. And when that peak is large, it has a potential energy of a large quantity. If it's small, then it has a smaller one. So the potential energy is proportional to the peak size of the peak, and inversely proportional to the wavelength. All right, let me explain this about the wavelength. Energy is proportional to the number of peaks per time. In other words, now I'm going to talk about how many, if I'm going to take an interval of 1 second, how many, in that frequency, how many times does this thing hit? Because the more it hits in that interval of time, the more energy. So energy is proportional to the number of peaks per time. High frequency or short wavelength light has many hits per time. Low frequency or long wavelength has fewer hits per time. Now the high frequency short wavelength has small peaks, so you can see why the energy would be low. Whereas the low frequency long wavelength has fewer hits per time, but out there it can have a larger peak. So that's at the other side of the right side of the curve. You get large peak, but it doesn't hit as often. So you got these things. You've got the size of the peak and the wavelength competing against each other. So these are two curves. This is the same one I just showed you. This is the lambda, the wavelength. I didn't go to 3, but this does. It goes from 1 to 0 to 3. But this is inverse lambda. Because in the equation, I'm taking the peak, I'm dividing it by lambda, which is the same as multiplying it by the inverse lambda. This clearly shows that at high frequency, short wavelengths, the number of hits here is high, and it gets lower and lower as you go out. So the product of these two, which is the same as the equation I just showed, what gives me this curve. This is the equation. Size of the peak divided by lambda gives this curve. You know, my peak of 80, my mode of 80, my peak of 100, and all of this is totally arbitrary. So I don't expect that this is, I can't match the values of this in any way. This is why I call it a preliminary analysis, just proving the point that the concept of high frequency, they have to have small peaks, gives you this fall off. And then after that, you get this fall off. The fact that it's even shaped at all like that is, to me, amazing. And I have very little data to go on to actually try to convert this into a precise waveform. There are empirical equations developed by people after Max Planck did his work and so on. These empirical equations do try to simulate precisely this. By the way, I don't have temperature in here because temperature is constant. But if I did temperature, if I did reduce the temperature to 4,000 Kelvin, then the reason this shifts to the right is because the atoms in that cavity are vibrating slower, and therefore the mode is lower. At higher temperature, the vibration is faster, and the mode frequency mode is higher. Than for 4,000 it's slower, and for 3,000 it's and that's what causes the shift from here to there. So here's my conclusion. Using TPM light, the concept of a detectable wavelength and a detectable peak, the ultraviolet catastrophe can be explained without quantizing Planck's equation, or for that matter, my equation. I didn't put a quantizing effect, but the equation, if we ever develop my equation a little bit more precisely, I would be putting limits on it. I would have summations with limits in certain ranges to accommodate the theory. As long as the equation, those limits match the theory, then you have a valid physical equation for that phenomenon. Without a physical model for light, Planck had no way to solve the problem. So he made what he considered an outrageous hypothesis, that for every mode of frequency, the energy in the cavity can only exist in lumps or quanta of size EF. Okay, that's the presentation, but I plan to do some more experiments. I am currently working on a setup to prove that the magnetic field is a spiral, not a circle. And eventually I hope to work with a double slit detector where the detector has an adjustable power dissipation that can affect the diffraction in different ways. Oh, come on, Bob. My name is Bob D. Hilster, and I am your particle guru. If you have any questions, ask particle.